Marissa, is there a Zoom link for like Zoom?
Oh, it's on YouTube.
It's on YouTube.
Yeah.
Is there like a name for it or anything like that?
I'm gonna post the link. All right, I put the link on like the main content page at the front.
We'll just do next week, right? Chapter 9 homework.
Yeah.
Oh, okay. I was confused.
All right, let's start off with just a little, well, actually, before we do that, so just a reminder that tomorrow is the Science Expo, so if you want to volunteer for that, or, bring your family, bring the kids if you want to come as well. So it's from 10 a.m. to 2 p.m., and if you volunteer, then you get 10 points extra credit. So even if you didn't make it to Monday's meeting, you can still come. So Monday's meeting was just more for kind of like training people. But if you just want to come, help out and, jump in where you can, go for it, more the merrier. Or like I said, bring your family, bring your friends. And so that is tomorrow. And that's just the third floor of this building. All right, so let's start off with a warm-up. And so see if you can draw the MO diagram for CO. And so just as a slight hint, not that this matters too much, but the more electronegative element should be lower. And then and I'll go ahead and tell you that yes, SP mixing is okay for CO. That one's. And so working partners, if some of you want to come to the board, we can come to the board, but I think I'll walk around and kind of see how y'all are doing. Because you really want to make sure you understand kind of your MO diagram and then what's going on and how to draw it. And if you're in the chat or watching later online, I would just take this time to draw your CO diagram as well. Oh, and then make sure you grab the homework since I made a mess on Tuesday. So it's just a single sheet, chapter 9 homework. Yeah. That'll help you. Well, then you're missing.
Looks like I was right on time. Yeah, yeah.
Yeah, well, I gave a hint, but, so the SK mix ones are the N2 and lithium, and then oxygen, chlorine, neon, and what? This one was weird, right, because it's carbon, oxygen, so that's two mixing. So yeah, it has to be the SK mix one. Oh, it was good. Yeah, yeah, because remember this one also becomes like non-bonding it, because the overlap in the center is canceled out. So even though they're formally in the bonding state, the electron density is small. Well, the high interaction with overlap, so it's more favorable and lower in the SK next state. Diagram. Yeah, well, no, yeah, electron still in. Oh, actually, it does work. The only thing is I like kind of seeing what's kind of together. Yeah. Yeah, now you just gotta like retranslate. So that's the thing of this kind of stuff, is like what orbital does it take? But you at least got the lines in the right order. Yeah, because it's a SP mix.
I'm just going off of the energy level as much as I'm. So, how So it's not, it's that strong, so when I this, I and then below, I'm on the equal to that. So basically it's the stronger, no, stronger one, so maybe.
Carbon or oxygen.
No, it is like a spatial body lined up, but because it's equal little lined apart, so I think it's like it's less favorable than what I guess by drawing your eyes thinking right here. That's why the title one is below this one. Way up more this. And then water structure. This is with S. Okay. So
I gave you the hint for C.
Yeah.
It just has like.
Yeah, it's understanding what you just want to understand what all these lines
Or not all of us, but give all.
These are pairing each other, I see. And then these.
And this one got here.
I see what you're doing.
Yeah,
These are basically pairing.
essentially. But it doesn't specifically have to be able to check the two, it's just always one. They basically and then and so now that you have bigger like carbon it looks kind of like this anti routine equation just higher energy electron.
Yeah, yeah, and your textbook is gonna be more like precise with pointing and series and how you compare across, but we don't need that much. We just care about order and timeline.
Something like that.
And
Yeah.
we try to use
Like,
this
they're
that
important,
are
like, I have to take a bunch.
negative marks start getting more.
I want to see if I'm right.
Yeah, and since we don't have any numbers, right, just like a little bit lower.
I mean,
Like we're just
yeah,
gonna
if they
just
have,
approximate
our,
within that
yeah,
range.
carbon test
But I
studies,
don't know.
yeah, you're right.
Yeah. That's pretty much the price. Go look at those, them all.
All right, let's kind of go through this together. So I saw a lot of good things. I just wanted to, let's draw it all together so we're all on the same page, because there's still a few fuzzy parts. And so, right, let's just talk about again, what are we doing with these MO diagrams, right? What are we trying to even find out? And so where Tuesday's lecture took us is, okay, we started with our Lewis dot structures, right? And they give us kind of an idea how things react and behave, but we saw it fail, right, for oxygen. So it's not a complete picture. And then, well, right, we learned that the Schrodinger equation, we can't actually solve it, right? We can barely solve it for hydrogen. So how can we solve it for, even CO? And so now this is where our MO theory comes into play. And so instead of solving for Schrodinger's equation, how can we look at these orbitals, right, and then try to figure out which ones are in the right kind of, like they match pictorially, that they can bond. And so that's where we're going with this. And it's really useful, and we'll take a look at some transition metal complexes later and see, right, it still tells us a lot of information without having to solve or do any math. All right, so how do we start our CO diagram? So I said to invoke SP mixing, and so let's just start off. So we always want to show kind of, I call it, right, who's coming to the table and what orbitals are interacting. And so we have our p orbital, so our 2p for our carbon, right, 2s for carbon as well. And then, so I try to give you the hint too, since we didn't talk about it, but the more electronegative element should be a little bit lower. And again, we don't have numbers, right? So it doesn't really matter, we're just estimating. So I just put it a little bit lower. Again, you could have put it more dramatic, doesn't matter. This is our rough calculation. And so now what's our lowest orbital? Who can describe that for us? What's it called? What is it? Yeah, so our lowest one here. So ignoring the core, but sigma, right? And so that's our 2 sigma. And so if we're doing SP mixing, so we have, right, our SP mix orbital. So kind of draw them really in phase. Right, so this is our SP mix most favorable orbital. And so then what's the next energy level? So now our sigma antibonding, and so that one was where they were out of phase, right, but the electron density was more on the outside, so trying to minimize that bad antibonding reaction. And so all I'm drawing here, by the way, is the SP mix orbital. So I just want to make that clear, right? So we could draw SP mix. Yeah, if you have the labels, that's fine. I just keep drawing the pictures. It's more for my sanity as well. All right, and then what's next after this orbital? So our pi, and so right, that's the key difference. So go back to the notes, and I did figure out the live notes. So now if you go under the chapter 9 for this week, they should be live updating. And so this is, again, right, your cheat sheet. So we said anything down here, right, is SP mixed. That's why we had that order change. And we can go over this again, individually if we still don't quite understand all the mixing and how those orbitals came together. But the quick and dirty is, right, we can just copy these orbitals, and that tells us the correct order as well. And so there's our sigma. Oops, now I lost myself. So our pi, just like you said, so our 2 pi, so our px, py we're calling it. And then what's next?
Oh, and it's not so it is in phase, but it's only a little bit, kind of.
Yeah, so right, electron density, so they're in phase, but we almost call it non-bonding, since, right, there's no electron density there making a bond. It's pretty minimized, but yeah, just like you said, it's on the outside instead. And then what comes next after this one? Now our pi anti-bonding, excellent. And that's right, px, py. And then what's our last, worst one? Yep, so we'll just call it, so now we're just going in order, right? So we started with 2 sigma anti-bonding, so now this would be our third one, and third sigma anti-bonding, but like you said, from our right pz and our s mixed orbital, and yeah, the very bad combination. Excellent. And then, so we're only looking at valence electrons. So how many electrons do we have in the center? So 10, so 1, 2, 3, 4, 5, 6, 7, 8. Oh, I skipped one, didn't I? My bad. I didn't start at the lowest one. Sorry. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so what can we say now? So where's our HOMO? So our 3 sigma, so we can say this is our HOMO, so our highest occupied molecular orbital. And so this is probably involved in bonding. So again, kind of giving us a hint, electron density on the outside. And we've seen, again, CO acting as a ligand. So this kind of explains that behavior. Excellent. Questions on this MO diagram? So let's look at the next sections, and we've kind of talked about this before, but I think we just want to continue to practice drawing and kind of make sure we understand for ourselves what's going on. And so all this is showing up here is just basically how we get our sp orbitals, right? So it's showing you our possible mathematical combinations. And so let's just break this down so we understand what it's trying to tell us. And so basically it's saying, and I like the shaded way better, but right, we have our pz orbital, it would be in this case, since we're mixing them. And so right, we can have pz that looks like this, where one side is shaded and the other side is unshaded, so they have it there, right, positive, negative. And so it's saying, let me fix the shading so I'm the same. So positive is shaded with how I'm going with this convention. Again, doesn't matter. But what we're saying is, right, this ball kind of cancels out this one and makes a small lobe here. So this is like half of your sp orbital. And then the other mathematical combination would obviously be where they could add, where the shading's the opposite, right? So now, basically, the unshaded side cancels out in the middle here, giving us, right, that overall sp mixed orbital. So kind of, right, combining those two, that's your sp mixed orbital. And so that's just showing you, right, we get this overall picture, but this is detailing really, right, the mathematical combination, because we have to consider both possibilities where we add them, right, where the kind of closest parts are in phase on this side or they're out of phase on that side. So giving you, right, this kind of larger lobe on one side plus a larger lobe on one side gives us the overall sp mixed orbital, which we just draw kind of over exaggerated like that as well. So we kind of ignore the little middle thing. And so now go ahead and draw out beryllium H2 here like they've done. But go ahead, right, label all your orbitals, think of what's coming together, right? Hydrogen only has our 1s as well. And then compare that to beryllium F2. Yeah, question?
In our MO diagrams, we've been able to do between two atoms. What if, like, we wanted to do beryllium H2? How would we do that in our MO diagram?
So it kind of depends for that one. So if you were doing beryllium H2, this is where that symmetry comes into play. And so what you do is, like, I don't want to get too into it because it's like a whole other course basically, but you can write the little ligands as what comes down to irreducible orbitals, so basically like kind of what patterns they belong to, which end up matching with like the orbitals, and then you can construct a diagram that way. But yeah, it gets a little bit more complicated. But right now we just want to draw kind of the pictures, so we don't need to make an MO diagram for this one. That's where it comes into play. And so I'll come around and kind of see what orbitals we're drawing. Oh, and there were a few people that were out last week that didn't do the welcome assignment, so if you could do that. I'll try to remember who didn't do one. You did one, right? hybridized orbitals. Then we have our 1s coming together. And of course, right, you want to talk about your pi orbitals, right, label them, y, pz, and then compare. So what's going on, right? So now we just have our fluorine, and it's just showing one 2p orbital. And you could also think about like why that is. You could draw the Lewis dot structure for fluorine even, right? Fill in the electrons, kind of see, well, what orbitals are even available? Because you have, probably fluorine has a bunch of filled orbitals, right? It has 3 lone pairs, and then 1 lone one. And so we're really just seeing that 1 lone one in the p orbital.
So those three that come out, those are all SP hybridized orbitals,
So
except the gray.
yeah, only the gray is sp and the regular, blue ones are the regular. And so I think y'all are seeing it, but let's just kind of talk about it together. And so we could even start with just a simple Lewis dot structure, right, of fluorine. So this is what I was kind of getting at. When we have, right, our Lewis dot structure, we could also translate it to this representation, right? So what is this telling us? And so if we think about it, right, so what this is saying, so we have electrons occupying, right, our 2s orbital is filled on fluorine, we know that. And then again, we don't know who's who, but we'll just call this px, py, and then assuming that our empty one is pz, right? So that's the one that's going to be making the bond here. And so that's part of what I was getting at is, right, keep in mind who's coming together. And so this is a lot simpler structure. of the hydrogen, so the beryllium dihydride. And so yes, I just wanted you to redraw it so we can clearly feel comfortable about what's going on. And so with our hydrogen case, we had our sp hybridized orbital, and then that left px, if we want to call it, and py, just like they drew out. Right, so just like that, the blue lobes are px, py, and then right hydrogen just has the s orbital, so that's a lot simpler. So just our s, and again, right, that head-to-head interaction is our sigma bond.
Is it just the positions of the hydrogens that makes beryllium an sp orbital? Or how is beryllium become an sp orbital?
Well, it's sp back, so we could, take it back to kind of our Vesper geometry where we said if it has two things attached to it, it's likely sp hybridized, right? Just because it's in the plane. We could also think of it, right, the s orbital and that pz are all in that axis, so that's why we do that sp mix there. Does that make sense? Yeah, because it's all about what's in like the correct phase there. But then if we compare that, so versus, right, our fluorine, and so let me try to do my artistic skills. So again, we have our beryllium sp hybridized, and beryllium, right, only has 2 electrons. And so they would be, right, in phase, so now they have to be in phase with this. So sigma interaction. And so now your book doesn't show this here, right? So this is where we have our bonding. But if beryllium, right, so beryllium only has 2 electrons. And so what does that tell us about these orbitals of beryllium? They're, what, unoccupied? Yeah, so they're unoccupied. And so this means that there could be, and this is going a little bit beyond this course, but this is kind of where I'm trying to get y'all to look at, well, what about our other fluorines, right? So they're still occupied, though. And so now let me try to draw this. Right, so we said our fluorine PZ, it's involved in this bonding here, right? They're sharing electrons with our beryllium. So beryllium has, right, our 2 electrons in our sp hybridized, so 1 going to our bond with fluorine, 1 going to our bond with the other fluorine. But then we may have what's called pi back bonding interaction. And so what that means is, right, if our fluorines then have electrons in there, so I'm trying to show that they're occupied, then there could be some sort of interaction and pi bonding with the empty orbitals of beryllium.
Did you say pi back bonding or back bonding?
Back bonding, yeah, back.
Pi backbone reaction cycle interactions earlier. Does that have anything to do with pi back bonding? Looks like pi backbone reaction.
Yeah, probably they're referring to like anytime you have a pi system. And so that's back what I was getting at with like the nitrogen, like how do you know what what the hybridization of nitrogen is? Well, it kind of depends, right? If there's some sort of pi system reaction, then.
And that pi system could be called a backbone.
Yeah, I haven't quite seen that term, but.
That was what I read in Wikipedia. It might just be something.
Yeah, you can show me exactly what it was saying. But yeah, this is called just pi back bonding. Just anytime you have the p orbitals, then they can interact with empty orbitals. And so, like I said, your textbook didn't go into this, but that's where kind of higher levels of chemistry go. But, right, even at our kind of intro level of chemistry, we can still get a lot of that information. And I want you guys to be thinking about that. All right, I'll try to speed it up a little. And so again, it's just going through the mathematical combinations of how we get our sp2 hybridized orbital, trying to emphasize, right, how we make our little ball in the center by getting rid of all these negative signs and then over exaggerating, right, the positive signs. So this is a good picture, again, of like the math behind it, since you have to have, right, both mathematical combinations at all times. And so same thing with this. Right now it's just showing our sp3 hybridized orbital, which we kind of talked about. And so again, this is a recap. But if you need to take time and, right, redraw these later, that would be a good thing to do. So I'm trying to finish up so we can do our quiz, but maybe after you do your quiz, right, you can go back, make sure you can draw these orbitals, can see what's going on. And then, right, we mentioned those double bonds. Again, we just want to emphasize there's no rotation. So we did cover it last week, but this is just a good reminder, right, that we can't have rotation with our double bond, because then we'd be messing up that pi bond. And so we could draw, I think we did formate last time. And so the key with formate was those were two sp2 hybridized orbitals. So, right, our oxygen is sp2, our carbon is sp2, and then we had our empty pi orbitals. So both have empty P, we'll just call it Py for a pi bond. So, right, anytime we see a double bond, we know we have a sigma bond, but then we have to figure out where did that pi bond come from, so what orbitals are involved. And so this is just, again, a reminder why we have the two isomers, right, why we can't just rotate, because, again, that double bond, so we would have to break it by some chemical process, usually take it to a single. Then you can rotate and break that and then reform a new isomer. And so again, same thing with triple bonds. So I think we looked at this with CN, so very similar with HCN, but we want to, again, see where our triple bond is coming from. So I did want to get into and at least kind of talk about some of these metal complexes. Sorry, I had an MO diagram pulled up and I lost it. And so last week, I kind of mentioned, right, we had benzene. So does everybody remember benzene, what benzene looks like? Yeah, so the ones with the double bonds, so we draw it like this, kind of abbreviated. And we could also, of course, draw it where the double bonds are like this, but like we said, we could rotate the double bonds. And so now if we look through, and so now this is kind of showing you and getting into kind of more complicated structures. So this is kind of goes into how do we do MO diagrams. And so it all depends on what pieces you have together. And so I wanted to try to show you the diagram of this compound. So it's bis-benzene chromium, which means we have chromium kind of sandwiched between two benzene rings. And so these kind of sandwich arring complexes are pretty common in chemistry. I think you can actually buy bis-benzene commercially. So it depends. A lot of these aromatic ring compounds you can either make, and their synthesis is well known, or apparently like this one is commercially available. Like ferrocene is also really common. And so let's kind of at least try to appreciate where these MO diagrams kind of come from. And so this, let's look at, and so their MO diagram is like a little crazy, at least from what we're used to right now. But let's try to break down kind of the pretty pictures coming together. And so these, right, are our pi orbitals, right? So we mentioned our p, what are we calling them, PZs? So these are all our p orbitals. And so just like this one, they're all in phase. And so this is the most symmetric combination where it has no nodes, right? So they're all the same phase. And so kind of the pretty picture, and so this is a good representation. And so now we're saying, and this is our metal, right? So this is our metal chromium. And again, we're just matching kind of pretty pictures. And eventually you would go on to know what these little symbols mean. But again, all we're taking away is, well, my s orbital can be the same shade as these p orbitals, and they can come together. Or my metal z orbital, notice, right, the shading is the same. So the z squared has your donut, and then the ends are the same shade. So that can be in phase with a benzene. So this is your bonding orbital. Or it shows, right, our other possible combination. So it's just showing you all the combinations, right? Or we could have, if we have a metal PZ ligand, right, so this is our metal PZ orbital, it can also bond with our benzene. And both of these have no nodes. It's just this was a combination of where the shade is on the inside, and this is a combination where the shading is different. Does that make sense? Do people at least see this so far? And so that's what these things are useful for. And so if we go to this next level here, and so again, this is just, it all boils down to a bunch of math, but it corresponds to this next level. And so notice now we have one node. And so these would be degenerate, right? So these two are the same energy, so they have one node. And so again, right, the node, notice they have opposite shading on opposite sides of the node. So on this side, right, they're all shaded. This side, they're all unshaded. There's our node separating them. And then if we go back to this MO diagram, all we want to take away is, yes, these different combinations, right, match up with different orbitals. And so, right, this matches with like our YZ or our XZ, again, depending kind of on the shading, or these kind of match with our P orbitals. And then that just goes on. So then the next one is, right, the next combination. So now we have two nodes. And then again, just what matches pictorially. And also, so you would also work out mathematically, but it's still kind of pictorially. But again, this is beyond our scope here. But basically, like, how do the pretty pictures match up? So the pretty pictures match up with these d orbitals. So our xy and x squared minus y squared. And then they go on to make our diagram, which is basically the same labels can bond with each other. So this is obviously way more advanced, but that's kind of where we're going. Yeah.
Is it similar to the structure of carbon fiber?
I don't think so. Yeah, so carbon fiber I think is more like amorphous or something. Yeah, because these are more like discrete compounds. Yeah, because other analogs to this would be like ferrocene, if I can spell it. So ferrocene is a pretty a famous aromatic sandwich compound. But sorry, what? Repeat. It kind of depends, and I guess, like, so ferrocene is pretty stable at room temperature, but it all depends on, like, each compound. They can all vary widely. Some sandwich compounds are, like, extremely air sensitive, so it goes into. Anyways, that's kind of where it's going. I also had another picture, if I can find it, since you did ask the question. So I wanted to show at least a diagram of H2 and kind of see how that would go. Again, you wouldn't do this in this class, but kind of what you do is you come up with like the mathematical ball representations, and so you have your substituents, and you write like all the mathematical possible combinations, so either whether they're both in phase or out of phase. So for beryllium H2, it's simpler because there's only 2 combinations, but once you go into 3, 4, 5, obviously it gets more complicated, but right, it's always like the same thing. It's like, are they in phase? And so, right, we have our s orbital is going to make a bond there, and then we can see, right, our pz is also going to bond. And so, right, it's showing us the same information. So we said by our Vesper theory that it's sp hybridized, and then when we see the MO diagram, right, it's showing us kind of the same thing, that our s orbital is in phase and our pz, and you could also maybe invoke some mixing, but again, that's just kind of where it's going and what you can look forward to and the power of the pretty pictures. All right, we'll stop there, and then I'll hand out your quiz. Of course, you can take a break if you want to take a break before looking at your quiz. So your quiz is all geometry and polarity, so you probably want your Vesper cheat sheet to help you with your geometry. And once you're done with the quiz, I would just ask questions if you're still fuzzy about this, so we can just talk individually. That's probably the best thing, and try to figure out your understanding. And the best thing to do for this chapter is draw and keep drawing.